Hi, and welcome to a Calc 2 video where we are going to work through some trigonometric substitutions within an integral so we can evaluate the integral. So let's look first at sort of the problem at hand here. If we have something like the square root of x squared plus 1, we are stuck with our algebra. There is nothing that I can do algebraically to simplify that because I cannot write it as some quantity squared, so then I can take the square root of it. Remember, we can only take the square root of one term, so if I have two terms under here, the goal would be, let me see if I can write that as a perfect square, and then I can remove that square root. So let's see how trig can help us with this. How can I take two terms and turn it into one? Well, trig helps us with that a lot, doesn't it? Do you remember the trigonometric identity or the Pythagorean identity, sine squared x plus cosine squared x is 1? So if I had exactly that, sine squared x plus cosine squared x, I could replace that with 1 or any other version of that. For example, I could say that I could replace sine squared x if I had the two terms 1 minus cosine squared x. So again, if I had the 1 minus cosine squared x, I could just put that one term in its place. Then I could take the square root of it. Okay, well, this was our first Pythagorean identity. The other two come from just a simple division. So if I take that basic Pythagorean identity and divide through by cosine squared of x, so every single term gets divided by that, sine squared x over cosine squared x is tangent squared x. Cosine squared x over this cosine squared x is 1. And the reciprocal of cosine squared x is secant squared x. So again, if I have the two terms, tangent squared x plus 1, I can just replace it with one term, secant squared x, and now I can take the square root of that. Okay, well, let's start with the basic Pythagorean identity and do it one more time. So now I will divide every single term by sine squared x. So sine squared x divided by that sine squared x is 1. Cosine squared x over sine squared x is cotangent squared x. And the reciprocal of sine squared x is cosecant squared x. Again, these you probably memorized, worked with, and derived in a pre-calculus or trig type course. But we're going to need these for our trig substitutions because if we make the correct substitution, we're going to turn two terms, like I have here, into one term if I make the correct trig substitution. Okay, so we're going to need these Pythagorean identities, so we're going to hold them near and dear to our hearts. We really only need the first two, but depending on which trig you want to use, maybe you do use the last one. Okay, so I don't necessarily need you to memorize these trig substitutions, how I'm going to write them here, but I'm going to show you the three that I'm going to use, and I'll show you why I'm going to choose these trig functions. So first of all, I'm going to stick with three trig functions here. We're going to stick with sine theta, secant theta, and tangent of theta. Okay? So do you remember good old-fashioned SOHCAHTOA? So sine is the ratio of the opposite side over hypotenuse. So cosine of an angle is the relationship or that ratio of adjacent to hypotenuse. And TOA, so tangent, was the ratio of opposite over adjacent. So we're going to kind of pull all of the trig that we learned here into these problems. So first things first, I'm going to label the right angle and I'm going to label a theta so that I can talk about an angle and know which angle I'm looking at to know which side is opposite and which side is adjacent. So from that, I'm going to look at the square root that I'm given here. If there is this square root somewhere in your integrand, okay, somewhere in your integrand, and u substitution maybe isn't on our plate because maybe u sub wasn't going to work, I need to do something else. So I will make the correct trig substitution if I think about which side of the right triangle, if I'm just thinking good old-fashioned Pythagorean theorem, no trig yet, which sides would be a and x? So if you're adding those together, do you remember the Pythagorean theorems is the sum of the squares of the legs of the right triangle equals the square of the hypotenuse of the right triangle. So what I know is that A is going to be one of the legs, X is going to be the other, and again, because it's opposite and adjacent, we're going to use tangent. So I'm going to specifically say, let tangent of theta be, and I'm going to say which variable am I squaring. So if you look under your radical or in that radicand, I'm squaring X, and I'll say what constant am I squaring? That would be an A. So if I look at this, and if I think this is the correct setup, which is going to make my whole problem integrable, I'm going to be able to integrate it, then I should end up with that exact square root in my problem. So let's take a look. Tangent of theta is opposite, so this side over here would be opposite, or X, and adjacent will be A. And then really take your time and solve the Pythagorean theorem and say, okay, what is this hypotenuse? Well, it's the sum of the squares of the legs equals the square of the hypotenuse, so I would have to take the square root of it. But again, there's nothing wrong with coming off to the side and saying a squared plus x squared equals that hypotenuse squared. Oh, okay, I take the square root then of both sides. If you ended up with the same square root or the same radicand that you have in your initial problem, you know that the trig substitution you wrote is going to work for that problem. So I'm going to do this again with a different trig function. So I'm going to label theta and that right angle there. And I'm telling you we're going to stay with sine, secant, and tangent because I'll show you why at the end. There's a pattern here. So if I look at the square root that's given, the square root of the quantity a squared minus x squared, okay? When you're doing Pythagorean theorem, your largest side has to be the hypotenuse. So in this case, a has to be the hypotenuse. I'm subtracting from that one of the legs squared, right? Because if you think of good old-fashioned Pythagorean theorem, a squared plus b squared equals c squared, c is always the hypotenuse, and then a and b are just your legs, okay? So it's the sum of the squares of the legs is the square of the hypotenuse. So if you're subtracting, so I'll subtract this b squared over here, that has to be a leg squared. Okay, so the more familiar you are with Pythagorean theorem, the more this probably makes sense. So my hypotenuse has to be a. Okay, so let's figure out which side or which leg x is going to be. So I'm just going to say let sine theta equals, and we're always going to start with the variable that I am squaring in my numerator, so that's x, over a, which is my constant that I'm squaring. And let's see if this works. Well, sine of theta would be opposite over hypotenuse, and yes, we said a absolutely is our hypotenuse. So I know that x would be my opposite side. Had we tried let secant of theta be x over a, right? Because I'm always going to have my variable in the numerator. Do you have to? No. We have the reciprocal trig functions we could use, but I think it's a little bit easier this way because it solves for x quicker. So if I said let secant of theta be x over a, secant is reciprocal of cosine. So that would mean in this example, x is my hypotenuse and a is my adjacent, and x is not my hypotenuse because I already said a had to be my hypotenuse. So that's not going to work. So it is in fact let sine of theta be x over a, and so I'll label my triangle accordingly and see if this is going to work. So my hypotenuse was a, the opposite side is x, solve using Pythagorean theorem for the missing side, which would be the square root of the hypotenuse squared minus the leg squared. If that matches, right, this square root that I started with, then I know that this was the correct trig substitution and my square root will simplify. Okay, so I'm going to do one more. I know we haven't used it yet, but we are going to use secant in this one, so let me show you why. So if we just start with let secant of theta be, we're going to say what variable are you squaring? I'm saying x over what constant are you squaring? We'll say a. Let's label our triangle accordingly. So secant of theta is reciprocal of cosine, so this would be hypotenuse over adjacent. So I'll label that accordingly. My hypotenuse is now x, my adjacent is a, and I'm solving for a leg. Again, even if you just call that b or something temporarily, a squared plus b squared equals x squared. I'm trying to solve for b squared. Take the square root of both sides. That's exactly the square root that you have in your problem. Okay, so this I know, if I replace secant of theta for every x over a that I see, and I'm going to show you how to do that in a problem here in a second, I know that this problem will work. If you pick the wrong trig function, your problem is not going to necessarily work using trig substitution. So I will fill these in. We're going to use tangent of theta equals x over a. And if you wanted to solve for x, I would multiply both sides by a. So I would say let x equal a tangent theta. So I'll solve for x in the other two as well. I'll multiply both sides by a. So a sine theta is x. And I'll, again, same thing for the last one. I will multiply both sides by a secant theta. So again, I'm choosing sine, secant, and tangent specifically as those three trig functions because x as my variable will be in the numerators of my ratios, and it'll be pretty easy to solve for x because I just multiply both sides by a. So I'm strategically picking these three. Could you use cotangent? Sure, because cotangent just reciprocates that first ratio that we have, so it would have been a over x. Okay, so keep in mind what we're doing, kind of where we're going. We're going to do one problem from start to finish, and then I'll make some more videos so you can see additional examples. So our goal, if I'm looking at this integral right here, and it just says evaluate the integral, my first kind of go-to technique for integration is always going to be u substitution. Now, I don't know if I would necessarily write this down, maybe just watch this part, but if your u is your radicand, right, what's underneath that square root right there? Du is negative 2x dx, and that is not necessarily something I have. You might think you have x squared, but you really don't. You have x to the negative 2, so I'm going to say that is not the best technique. So u sub is not necessarily organically going to work, so I'm going to move on. So then I see, ooh, I have a difference of squares underneath my square root. So a difference of squares or a sum of squares, I am good to go. And let me make one last thing clear just so you know. The square root of the quantity 5 minus x squared is also a difference of squares because I am squaring square root of 5 and I'm squaring x. So truly every value, right, a constant value has a square root. It just doesn't necessarily mean that it's whole. Okay, so let's do a trig substitution here and see if we can make this work. You could memorize, if you were so inclined, that if you have a sum of squares, you're going to use tangent. That might actually make sense if you think back to Pythagorean theorem, because a sum of squares, you're solving for the hypotenuse, so you're given adjacent and opposite. Okay, so then maybe the sine and the secant are the ones where you think, well, I want to memorize. In sine, your constant is going to come first. If you use the trig replacement with the secant, the variable is going to come first, or the function is going to come first. So I can see in this problem that I have a number first. So what I think is I'm going to start with let sine theta, and I'm always going to do the same process. What function am I squaring? I'm squaring x. And what constant am I squaring? That's a 3. Now before you go any further, let's make sure we have the correct trig substitution, otherwise the problem will not work. So I strongly recommend you going over to a right triangle and taking this ratio over here. This is how you begin the problem. I will also use this to end the problem. So use basic SOHCAHTOA. If sine of theta is x over 3, that's my opposite over my hypotenuse. So sine of theta, opposite of that theta is x. Again, that's why you have to label your theta so you know which side is opposite. And the hypotenuse is 3. Now really take your time. So you can call this side whatever you want. I mean, I certainly wouldn't call it x, but I can call it a if you want and say, okay, a squared plus x squared equals 3 squared. Again, I'm solving for a. 3 squared is 9. If I subtract the x squared from both sides, then take the square root. So I can see that this leg will be the square root 9 minus x squared. If that is matching, right, so if this is matching the square root that is in your integral, it's in your integrand, then this is the correct trig substitution. If it does not match, you have chosen the wrong trig function. Don't continue. Change your trig function. Okay, so now I'm going to focus on this here. Well, I'm going to multiply both sides by 3 so I can solve for x. So every x I see, this is going to be the substitution that I make. So I'm going to have to put it down here for x and up here for x. But you notice I also have this dx. So I need to figure out what dx is. Well, take the derivative of your x statement. So dx would be 3 cosine of theta d theta. Because again, x is not necessarily theta, right? So if x is 3 sine theta, we have to be able to find dx. And I'm going to do my substitution in one step without any simplifying. I'm just going to write it all down. So it's going to be the antiderivative square root. This is going to be long, so I'm just going to start it and I'll finish it in a second. 9 minus the x is 3 sine theta quantity squared. There's the end of my square root. All over x squared. X is 3 sine theta. And then times dx. And just so I can really see and make sure that I'm substituting in that dx, right, I keep that separate exactly where everything was. Again, if you make an error, you want to be able to look back and see where your error is. Okay, this should simplify into a trig integral, and we should have just gotten done doing a section on trig integration. So I got to be good at that before I do trig substitution. But now let's see here. I'm going to simplify this a little bit. Square root of 9 minus 9 sine squared theta. That's where my square root ends. Over 9 sine squared theta. And I'm going to just copy down my dx, which was that 3 cosine theta d theta. Now here's one piece of advice, take it or leave it. I've done a lot of these problems, right? Both my own and trying to help my students find their errors. I'm going to look at all the constant coefficients at one time. And I'm not ready to do it now. So I'm going to just leave the values there for now. I'm not going to leave them forever. But if I try to divide things now, everything is going to be a 3 and a 9. And if I use something twice or don't take the square root of 9, etc., it's going to be really hard to find my error. So I'm going to do all my constant coefficients at one time, and I'm not ready to do that yet, so I'm going to leave them. Right now, I'm going to focus on this piece right here. And if I take that off to the side, 9 minus 9 sine squared theta, so 9 minus 9 sine squared theta. I'm just kind of taking this off to the side so you can see what this becomes. Hopefully you're able to see that I can at least factor out this 9. Well, now look what you have. Remember those Pythagorean identities from the beginning that I circled up here? Right? And I said, okay, great. Sine squared plus cosine squared is 1, but you can also solve it for either of the two trig functions, obviously squared, so you're turning two terms into 1. So if I had 1 minus sine squared, that's going to leave me with just cosine squared. So this turns into one term, which is 9 cosine squared theta. So I'm going to come back over here now and replace this, the highlighted piece here, with 9 cosine squared theta. And what did that really do for me? Well, remember we talked about you can't take the square root of more than one term. So now I have only one term under that square root. I went from 9 minus 9 sine squared theta, that's two terms, to 9 cosine squared theta, that's one term. So I'm going to take the square root of it. That's 3 cosine of theta, and I'll write everything else down one more time. It is also very important. Some people try to shorten this and don't write their angles, but especially for double angles and things like that, we need to make sure that our angles are the same. Otherwise, we can't combine these together. Okay, so now I take care of my constant coefficients, and you see how everything turned into like 3s and 9s. Same will be true for like 5s and 25s, right? So it can get confusing. So I just do it all at one time so I can trace it back to the problem. 3 times 3 is 9, divided by 9 is 1. So I would be bringing out a 1 as a constant coefficient. I don't need to do that. And now I have antiderivative cosine theta times cosine theta would be cosine squared theta over sine squared theta d theta. And this is where we have a trig integral that hopefully we mastered from the previous section. So I recognize this one because cosine squared over sine squared is really just cotangent squared theta. And why does that help? Well, because I can integrate cosecant squared theta, right? I know who the antiderivative of cosecant squared theta is negative cotangent theta, right? I know that part. Okay, well, but I don't know cotangent squared. But you do because you have that beautiful Pythagorean identity over here. Let me find it, right? You have this Pythagorean identity that says cotangent squared of any angle would be cosecant squared of the angle minus 1. So that's what I'm going to substitute in here. So I'm going to change this to be, instead of cotangent squared theta, cosecant squared theta minus 1. Antiderivative of cosecant squared theta we talked about is negative cotangent theta, and I'm anti-differentiating 1 with respect to theta, so that becomes a theta plus c. Now I'm going to copy this underneath my triangle. Negative cotangent theta minus theta plus c. So I got negative cotangent theta minus theta plus c. If you will recall, the problem did not start with thetas. The problem started with x's. So if I have bounds, I definitely would change my bounds to thetas, and I could put thetas in now. This did not have bounds. This was an indefinite integral, so I do need to go all the way back to x's. Well, what is cotangent of theta? You have a right triangle. You know all 6 trig ratios. So cotangent of theta, if tangent is opposite over adjacent, cotangent of theta would be adjacent over opposite. So this will turn out to be, with of course the negative out front, adjacent of the angle is that square root of 9 minus x squared quantity. Opposite is x. In theta, you actually have 6 different ways of writing theta out. You started this by saying let sine of theta equals x over 3. So if you do have to solve for theta, one easy way would be to take the inverse sine of both sides to solve for theta. And I could say theta is inverse sine of x over 3. I could have also said it's inverse of cosecant and reciprocate that, so 3 over x. I could have said it's inverse tangent of the opposite over adjacent, so I could have said inverse tangent, the opposite is x, the adjacent is the square root. So there's really 6 different options for that theta. Again, I just go off of the one that we wrote from the beginning because that usually uses the least bit of difficult stuff. So here's my antiderivative back in terms of x evaluated. Don't forget your plus c. Again, I will repeat, we're going to choose sine, secant, and tangent, and that way the x's are all in the numerator of that ratio, and I set up my triangle accordingly. So if you start your problem with let sine theta equals, secant theta equals, tangent theta equals, you'll be good to go. The only thing I'm going to do is scroll to one more problem and just take a look at a setup, and then certainly you can watch the next video to see how to solve it. So I see a sum of squares under a radical. Use substitution, I've already gone through in my head or processed through, it's not going to work. So I'm going to say I have a sum of squares. I'm going to start this problem by saying let tangent of theta equal what I'm squaring with the variable or function, so that's x, and what am I squaring with the constant, that would be a 2. And from here on out, the problem should work, and I should get a really nice trig integral that I can then evaluate. The square root will go away, in essence, because I can take the square root of one term. So I hope you found this video helpful, getting you started with trig substitution for integration. Thanks for watching. More videos to follow.